Continuamos então? Bom, então... Oh. Sorry. Have to switch, right? Press the button. English. Okay. So what we were studying here, right? What is the behavior of the optimal solutions and optimal values, right? When you have this sample approximation of the functions, right? And so, at least empirically here, we are seeing that it seems we do have convergence, right? In some cases, like in this case, we don't, right? In fact, we saw that we were oscillating between two solutions. That was the case when we had these multiple optimal solutions, right? Okay, so how general is that, right? So let's see what can we say in general. So we can see the comment that we were making before, right? So it turns out that what the key here is really the fact that we have uniform convergence, right? So if you don't have a uniform convergence, it's easy to construct some counterexamples, right, where things fail, okay? But under uniform convergence, everything works well. Either uniform convergence or, more generally, if you have epiconvergence, even better. Okay, so we have epiconvergence, which epiconvergence allows to show convergence in broader contexts. So here's the result, right? So one first result is the following, right? So if you have uniform convergence, okay, then it's possible to show the following. First, that the optimal values will converge to the true values. The optimal value of the approximating problem converges to the true value of the true optimal value with probability 1. Right? Meaning, regardless of the sample path, right? No matter which sample path you pick, we have convergence for as n goes to infinity. And here is going back to those compactness assumptions, right? So suppose there's a compact set, right, that we can that contains the set of optimal solutions. Okay? So in other words, the optimal solution, this is not an unbounded problem, for example, right? Where the set of optimal solutions could be unbounded. So if you have this condition, right? So essentially this says that, so if you have a compact set that contains the set of optimal solutions and contains the set of approximating solutions for n large enough, essentially this is saying that, well, my problem, I could think of my problem as completely constrained, right? Into this compact set C, right? So if my whole problem is inside a compact set, the whole feasible region is contained in this set C, then we can guarantee that solutions will converge as well. Okay? So we say that the objective function, and the second hypothesis here is that the objective function is continuous on this set, okay? So if you have continuity of the objective function, okay, then what we can say is actually that the distance between the set of approximating solutions and the set of optimal solutions goes to 0. Okay? Well, what is this distance here? You can see this, you can interpret this distance as, for example, the Hausdorff distance between two sets, right? It's the maximum of the distance between each point on one set to the other set, okay? So that's the Hausdorff distance. So essentially this is saying that this whole set here, Sn, converges to the set S star. So this is nice, right? So we have actual convergence of the whole sets. They go, and it goes to, that distance goes to 0, okay? So the key here is really to have uniform convergence. Now, when can we ensure uniform convergence? In many different contexts. For example, if the function is convex, there is a uniform convergence. Essentially what we need here is what is called the uniform strong law of large numbers, right? So we need the law of large numbers to work uniformly for each x, right? So this is guaranteed, for example, if we have if the functions are convex. That's one case. There are a multitude of assumptions, different assumptions. For example, I think if it's the function is Lipschitz, also this will hold. There's different settings that one can ensure this type of uniform convergence. If one does not have uniform convergence but still has epiconvergence, that will work as well. Okay. Now, what convergence with probability 1 means? Well, that means that regardless of the sample path, we have convergence as n goes to infinity, right? Remember that the samples correspond to one particular sample path, right? So essentially the theorem is saying that, okay, no, it doesn't matter which sample path I pick, I always have convergence, right? So no matter how many times you do the same experiment, right, of drawing a sample and solving the approximating problem, it always will converge. Okay? Maybe different n's, right? For some samples will converge faster than the others, but will always converge to the right value, right? So that's at least reassuring, right? That as n gets large, we know eventually we're going to converge, right? So here's an example, right? So that's exactly what I did. I took the Nussbender problem that we were looking before, and now I fix n, right, 270, and now I'm picking different sample paths, generating multiple sample paths, right? So I think this was done for it was like 1,000 samples here, okay? 1,000 different samples, 1,000 different sample paths, right? Important to make the distinction here. So those are 1,000 sample paths, right? With the same n, right? Same n at 270. So you can see the function can vary quite a bit, right? For the same n. Sometimes it's this function, the other extreme is this function here. The same n, right? Of course, there's randomness in the sample. So even with n fixed, you could have different ones, right? So this is the whole fan of, this is with the exponential demand, and this is with the discrete uniform demand, right? So we can see in both cases, there's quite a bit of variability. Of course, in this case, each sample, in both cases, the function is polyhedral, right? Here we can see a bit less because the n is 270. The pieces start disappearing, right? It almost looks like a continuous function or a differentiable function. But there is still, each of them is still polyhedral here. Okay? But the true function is continuous. It's differentiable. Okay. So we can see, right, that for some sample size, we have a very good approximation, right? That there's the whole fan here. Some of these will be very close to the true function, which is underneath here, but some of them are far, as expected, right? Remember, even we did that simple experiment with the completion times, right? We saw that in some cases we could be very close to the average, but some cases we are far. There's some kind of normality going on, right? And that'll be the same here, right? Still some kind of central limit theorem applies, but think of this in terms of functions now, right? So one way of thinking of this is think of this as a functional version of the central limit theorem, right? Which in fact was one of the developers of this type of result was Aloysio Araújo, right? A familiar name here at IMPA, right? So he was one of the developers of this type of results where you have a functional central limit theorem, right? So you apply that for and that's what we need here, essentially to say, okay, we're going to guarantee that these whole functions have converged to some kind of Gaussian process, right? So that's how we can get asymptotic results. So that's kind of the idea of how these things are developed, right? So this is what we were saying, right? So the theorem guarantees convergence as n goes to infinity, but for a fixed n, again, we could be closer or farther to the true optimal, right? So sometimes we need a larger n to get the same quality, right? So if you pick one sample of size n, anything could happen, right? If you pick one size, or how do we know if we are on a good or a bad sample path, right? Well, we don't, right? There's no way of knowing. Right? If you pick one sample path of size n, and we solve this problem, there's no way we can say, well, this solution is good or not, right? Because maybe I was unlucky, and that particular sample path was converging only for n equal to 10,000, right? That was just bad luck, right? Or maybe it was one of these functions here, right? Like this guy, it's very far, right? Even with 270, this guy is very far from the optimal. For this sample path here, I probably need a much larger n until this function will start converging to the true one, right? That's the problem. So if I just fix n and solve this, yeah. So I can remember once talking to a colleague, right, who was working not in this area, was working a deterministic optimization, and then he asked, well, so this thing about sample average approximation is just a matter of replacing expectation with averages and solving the problem, right? That's all about it. No, it's not, right? And that's the problem, right? Because if you just do this, pick one sample, replace, and solve the problem, you have absolutely no guarantees whatsoever that things are going to work. Right? You could be extremely far from the optimal. So that's something to keep in mind, right? So we don't. So we need other methods. So the idea here is to use the same way that for the estimation problem, right? We can rely on the central limit theorem to get confidence intervals. Here we're going to need somehow, right, similar tools that can give us some idea of how far we are from the true optimal, right? For a fixed sample size. Okay. So that's what we're going to need here, right? Otherwise, it will be a useless estimate. Right? If you just solve this, it's a useless estimate. Okay? So we need to have some probabilistic guarantees. That's the bottom line. Okay? So in terms of rates of convergence, right? So here is again, still keeping the Niels-Vendor problem, right? In the background, right? So here's what we get when you look at the optimal values from these graphs, right? So essentially, I took this. These were like 1,000 experiments, as I mentioned, right, for a fixed n. And essentially, we're just doing a histogram of the optimal values, okay, that we obtained from this 1,000 experiments. And here's what we get, right? Interesting enough, right? We see normality, okay? So it looks like the optimal values seem to be normally distributed, right? So we know that the pointwise estimates will be normally distributed, right? For each fixed x, we know that the sample average estimate will be normally distributed. That's just the central limit theorem, right? But this is saying, at least empirically, right? This is saying more, right? This is saying that the optimal value of the optimization problem also seems to have a normal distribution, regardless of the initial, right? Here, we started from an exponential distribution. This is discrete uniform. And in both cases, we do see some kind of normality. Is that clear? Right? So this is quite an interesting observation, right? To watch these graphs and the optimal value and see normality. So when, of course, wants to ask the question, how general is this? Right? Do we always see normality in the optimal values? Right? Remember, we are talking about normality of, this is the optimal value, right? So this is what we are calling nu n. We are looking at the distribution of this as a random variable, right? For a fixed n, we are looking at how is this guy distributed. Okay? We already know that nu n converges to nu star, right? As n goes to infinity, and you converge with probability 1, right? But we are trying to ask a different question now. It's like, okay, if I fix n, what is the distribution of this quantity? Okay? So it appears we have normality, right? But is that always true? Right? And does that help? Right? Or why does that help? Right? Why having normality helps? Right? Well, let's ask, right? So why does that help? Suppose we are able to show normality, right? Why would this be helpful? If you can show normality of the optimal values of the nu n, why would that matter? How could we use this? For one thing, we might think of doing confidence intervals, right? Same way we did for estimation. What else? What else do we get from normality? Suppose we are able to show a similar result, right? As we saw in the other case, like square root of n, that nu converges to something, right? Divided by some sigma here that converges to a normal 0, 1, right? Suppose we are able to show this, right? Besides confidence intervals, what kind of information this is also giving us? It's the rate, right? If you can show this, essentially this is saying that, well, the rate of convergence here of these optimal values is 1 over square root of n. right? Because we know that when we scale this by square root of n, this converges to a normal distribution, right? So essentially, we can say that, well, okay, these values are converging kind of at a rate of 1 over square root of n. Right? So this gives us information on the rate of convergence. So, well, let's see how general is this behavior, right? So let's think again of a generic g function, right? Not the Niels van der one, but the generic one. So here's what can be shown, right? Again, results from the literature says that, well, if we assume, without listing, in detail all the assumptions, you can look at the papers for that. But essentially what you need here is some kind of compactness of the optimal, of the feasible set. You need Lipschitz continuity of the objective function, okay? And if the optimal solution is unique, then it's possible to show that the nu n, if I scale this by square root of n, right? This will converge to a normal zero sigma, yeah? Where sigma, the sigma of x, is the variance of g at x. Okay? So that's the type of result we would like to see, right? In fact, that's what, in a sense, that's what we see here, right? Here, the mean value will be close to the true optimal, right? And we have a normal distribution, and what is the variance of this normal distribution is the variance of the function calculated at the optimal solution. Okay? So we do have normality, right? So again, we can think of doing some. Constructing confidence interval is a bit tricky here because we don't really know this variance, right? Because we don't know what the x star is, but one can approximate, right? And there is some work on that. Well, and the idea, as I mentioned before, the idea to prove this, well, at least one technique to show this is using this functional central limit theorem. Okay, so one can view, just to give it, without doing the details, but just to give it the idea behind, right? Essentially, we can say that v, right, the optimal value is some function of the whole process, right? We can think of the optimal value as being some function of the whole process, right? So now, if we know, right, we have a central limit theorem in functional version, right? So we know that these functions will converge, right? If you think of the approximation, right? What we call the Gn, or little g, right? We have now Gn dot, right? Now if you apply phi of this, right? So if this converges in distribution to this, then the phi function, because it's continuous, the optimal value function is continuous, it will also have some kind of keep the normality, right? Under proper assumptions. So it's just to give an idea, how do we get normality, right? Of this, right? Because it's essentially saying, well, the optimal value is a functional of the whole function, right? So if this converges in, we have a central limit theorem for this guy, a functional central limit theorem, then, well, phi of that will converge to the phi of the one in distribution, okay? That's kind of a little bit the idea. Of course, you need proper assumptions to do that argument, but that's what is behind this normality, right? It's the functional central limit theorem behind. Okay. One thing, though, it's important, and the reason why I emphasize this word, this holds when the solution is unique, okay? When the solution is not unique, things are not as nice, unfortunately, okay? And here's what happens. Well, before mentioning that, well, the comments that I already made, right? So this is approximately normally distributed. We can converge this. We can information about the rate of convergence. So here's what I was going to say, right? So when the solution is not unique, it turns out that the result is, instead of convergence to normality, actually you have to replace the right-hand side with this quantity here, right? So instead of having a normal distribution here, what we have is the minimum of a bunch of normal distributions for all solutions in the set of optimal solutions. Okay? So think about this. This is taking the minimum of a bunch of normals, right? So is this going to be normal? What do you think? Is the minimum of two normals normal? No, right? In general, even if you take only two, right? You can do a simple calculation, right? Just take two normal distributions, you take the minimum of the two, you can clearly see that it's not normal, right? So here, imagine, even with two, imagine here you're taking the infimum of a bunch of normals over a infinite set, in fact, right? Because you have S star here is the set of all optimal solutions, right? So we can think of this as convex set, right? We are taking the minimum of all normal distributions, so this is certainly not normally distributed, right? So that's how it is, right? There is no normality. So the only reason we observe normality here is because the reason we saw normality here is because we have uniqueness. Actually, turns out that this case, it appears normal, but if you actually do a statistical test, you see that it's not normal. Okay, if you do like a goodness of fit, in this case, you see that actually the normal distribution is not a good fit. Okay, visually it appears to be normal, but actually it's not. This one is, but this one is not, because this one is the one with the uniform. So at least, so what we say, what we know, right, that this is the minimum of a bunch of normals, but this is not. So now we cannot rely on central limit theorems anymore, right, because it's the minimum of a bunch of normals, right? Unfortunately. So the case when you have multiple solutions is clearly more complicated, okay, compared to the case where you have a unique optimum. Okay. What else can the theorem tell us? Right? The theorem also gives us some information about the bias, right? So what is the bias, right? Think of this is our optimal value, right? So now remember that nu n was our estimator for the optimal value, right? Because this was the optimal value of the approximating problem. So one issue one can think about here is, okay, what happens when I take the expected value of this estimator, right? In the case of simple means, what happens, right? In the case of simple means, remember when we did that calculation, right? Suppose you have x1, xn, right? And then I take an x bar, which is just the average of these guys, right? Our x bar. So if I take the expected value of x bar, of course, this is just the expected value of x, right? The original value. So we can say that this is an unbiased estimate, right? So the sample mean is an unbiased estimate of, so this is, right, is our samples from a certain x. So the sample mean is an unbiased estimate of the true x, right? Of the average of the random variable we are going to calculate, right? Unbiased in the sense that the expected value is the true expected value. But here, turns out that this is not the case, right? If I calculate the expected value of nu n, this is not the same as the nu star. Okay, why is that? Well, let's see. Well, what's an implication of this, right? So in fact, if you solve the problem, one way to check this, right? Empirically. If you solve the problem, let's say 100 times, fix n, solve the problem 100 times, and take the average, it's always going to be below the optimal value, or most of the time, right? Especially if you take do enough experiments, right? So you suppose you do this 100 times, calculate the Vn for in each experiment, and you do the experiment 100 times and take the average of the 100 experiments, you see that almost all the time you're going to be below. In fact, you're going to be below the true value. Okay? You can even do that for the Niels-Wender problem. I encourage you to play with, like in MATLAB, and check that out, right? That if you just do the experiment many times, take the average, you see that you're going to be most of the time below the optimal value. Okay? So this is essentially saying that, well, there is a bias. So why is there a bias? Well, it turns out, I mean, it's easy to see why there's a bias, right? In fact, just take the case where n equal to 1. Right? Imagine that you only have one sample. Okay? So, well, then the expected value, right, of the optimal value is just the expected value of the minimum, right? Because that's the definition, right? Nu is just the minimum of the function, right? Well, but this is less than or equal to the minimum of the expected value. So why is that? Right? And then this is just the new star, right? Because this is the original problem here, right? So the key here is this inequality. But why is this? Why is this inequality true? Yeah? Yeah, good way of, one way of viewing it, right? So we can see that the minimum for each fixed sample path, right? The minimum of G is always less than or equal to Gx for any x, right? Because by definition, I'm minimizing this over x, right? So for fixed C, this minimum is less than or equal for any x that I pick here, right? Well, if that's true, and this is for any C also, right? Well, if that is true, then I can take the expected value on both sides, right? And this is going to be less than the expected value of Gxc, right? And now it's true for any x, right? Because the expectation is just an average, right? So if this is true for any c, it has to be true on average, right? Well, but this is true for any x. So in particular, now this is just a number, right? There's nothing varying here. This is just a fixed number, right? And this is true for any x. So I can take the minimum on both sides, right? So then the expected value of the minimum of Gx will be less than the minimum over x of the EGX. That's precisely Felipe's argument, right? Is it clear? So that inequality will always be true. And easy to see that this can be strict, right? In fact, most of the time, this is going to be a strict inequality, right? Because this one here, right, it would have to be true for any x. So I'm taking now another way of viewing it, right, to see why this is strict, is to think of this as being a sum, right? So the sum of the minimum is always less than the minimum of the sum, right? That's another way to interpret this inequality, right? Sum of the minimums is less than the minimum of the sum, right? Because if you have two sequences, right, if you have the minimum of an plus bn, right, this has to be, this is the minimum of an plus the minimum of bn, right? Minimum of an plus the minimum of bn is less than or equal to the minimum of right? This is also true, right? Because here you have more freedom, right? You have to take the minimum here and the minimum here. Here you tie to the same n, right? So in general, this inequality, it's the same principle there, right? So the sum of the minimum will be less than the minimum of the sum, right? So again, another way of viewing this inequality. So here you see why typically this is going to be strict, right? Because the minimum of each one, you have much more freedom than on this side, where you tie to the same one. So most of the time, this is going to be strict, okay? Well, the good news, right? So I mean, you did this for n equal to 1, but exactly the same argument is valid for any n, right? Especially this argument here, right? It's true, instead of working with a single g, I can replace g here by the gn, right? And it's going to be exactly the same argument. So we conclude that it's the new n, right? So if I think of this as a new n, is always less than the new star in expectation. Okay? So there is a bias. Okay? So on average, the approximating problem gives an optimal value that is all below or at most equal to the new star. Right? So this might be, it leads to the surprising results, right? So I remember once a colleague also asked me that, saying, oh, I'm solving the sample average problems and I'm doing many times, I take the average, always below the real value. What's going on? Well, that's what's going on, right? It's just not surprising. It should be below, right? And just for any n, right? Well, the good news at least is that this bias, as you should expect, right? This bias should decrease with n, right? The larger we take n, the less we expect to see in terms of bias, right? Because we get better and better approximations, so we should get a smaller bias, right? And this is actually true, right? So it's possible to show, right, that this goes monotonically in n, right? The bias goes to 0 monotonically in n as n goes to infinity, okay? So which means that, well, if you compare this with n, nu n plus 1, the expected value of nu n plus 1 will be bigger or equal to expected value of nu n, still less than or equal to nu star, but it gets closer and closer to nu star. Okay, so that's good news. We know that the bias is shrinking. And what else can we want to say? In fact, just to give an example, right? So in the case of the Niels-Wender problem, so there is this paper by Freiman et al., right, where they do some calculations, exact calculations for the Niels-Wender problem. And yet, for example, when demand has uniform distribution on 0, 1, right, they show that the bias can be computed exactly as this. I mean, the bias is very hard to calculate in general, right, for a general problem. In this case, of course, the Niels-Wender, you can get, one can get explicit expressions, but generally speaking, it's very difficult to know exactly what the bias is, right? One can only have bounds on the bias, but getting an exact expression, it's only for very simple problems. So in this case, they show that the bias is order of 1 over n, for example, right? So the bias has exactly this expression, so this is essentially 1 over n. Okay, so the bias is shrinking fast, right? We know that the bias gets closer and closer to 0. Well, they show that in this particular case, it shrinks very fast. Okay. So, in fact, in general, the rate of convergence of the bias for a stochastic program can be a variety of values from n minus p, right, from p to minus half to infinity, in fact. Right? So this for some problems, the bias can go to 0 very fast, but the slowest will go is n to the minus 1 over square root of n. Okay, that's the slowest the bias can go. What is the situation where it goes as slow as that? Again, is the case of multiple optimal solutions, right? Why? Because remember that result. Remember that result we saw, right? That the optimal value converges at a rate, right? It converges to the infimum of a normal distribution, right, Felipe? Which random variables? Well, but it's not the infimum of a random variable, right? It's the infimum of a distribution. So this is like summing, like if you had 2, it would be the sum of 2 normals. Yeah, I see what you mean. If there's correlation between these two, the 2 normals. Yeah, I think they're independent, actually. But why would that help? Yeah, it's you mean why it's the minimum of the normals, or what's? Yeah. Oh, is this the minimum? Well, imagine your S star. Well, this would never happen because your S star has to be convex, right? In this case, but imagine that you had only 2 points, right? X1 and X2, right? Then this thing here will be the minimum between a normal, right? A normal 0, sigma 1, right? And a normal 0, sigma 2, right? Where sigma 1 is the variance at x1, sigma 2 is the variance at x2, right? So this is the minimum between two random variables, right? So imagine that, if you draw a sample path, right? Or let's see, if you think in terms of a histogram, what can we say here? It's easier to think in terms of sample path, right? So for each sample path here, right, each omega, right, you take the minimum between two of them, right? You take the minimum between this guy and this guy for each omega, right? And then you can see, okay, what is the distribution of this, right? Each of them are normal, right? But imagine that now you take 1 point from each one, and you take always the smallest of the two, right? And take a look at the distribution. For example, since you asked the question, right? A good hook to. What do you think you can say about the mean of this distribution? I suppose we could calculate this, right? This still has a distribution, but it's a weird distribution, right? But still, it's some distribution, right? What can we say about the mean of this distribution? Anything? It's the minimum of a bunch of normals that have mean 0, right? So what do you think we can say about the mean of this infimum? You think it's going to be 0 again? Wellington is skeptical. What do you think? Let's go back to Felipe's example, right? Only 2 variables, right? So imagine that I draw an experiment, right? I do an experiment where every time I pick 2 normals and I take the smallest of them, right? So you have 2 normal distributions. One is a 0, let's say, right? Both have mean 0, right? Both have mean 0, okay? But let's say one could have a sigma bigger than the other, right? So now I'm going to do the following experiment, right? I'm going to take a bunch of samples. And so I pick one sample from here, one sample from here, right? This is also 0. Take one sample from here, and take the smallest of the 2, right? And do this many times, right? Take one sample from here, one sample from here, take the smallest of the 2. What do you think is going to happen on the average? Do we get 0? No, right? We're probably going to get something negative, right? Because we're always taking the minimum of them, right? When I take only one distribution, I take samples here and here, right? And when I average them, of course we get 0. But now if you're taking the minimum of the 2, it's always like you're skewing things to the left side, right? Because you're taking one sample here. Any sample that falls on this side could be countered by a small sample here, and vice versa, right? So it's less likely that you end up with positive numbers. Do you agree? Right? Because you're always taking the smallest of it. It's like you're taking the worst case of the 2, right? So in this case, we can certainly say that this guy, the expected value of all this animal here is going to be negative. Uh-huh. Which the one that's saying that the expected value of the infimum. Yeah, good point. Yeah, that's true, right? This is the expected value of the infimum of something, right? And this has to be less than or equal to the infimum of the expected value, but this guy is 0, right? Good point. It's always less than or equal. But my point is that it's just that most likely this will be strictly negative, right? Because of this thing that we are taking the smallest of the two, right? So what is it saying? That when we have, so if this has a strictly negative mean, what is it saying about, now let's replace, right? We are looking at expectations. Now let's look at happens this in terms of expectations, right? Now we have expected value of Vn minus V star, right? Let's suppose some assumptions here that convergence in distribution implies convergence of expected values, right? There's like you need some uniform integrability for that, but let's suppose this holds. So this converges to something, right? Which is converges to something that is less than 0, right? Because we just said that this is the expected value. Let's put, right? This converges to the expected value of that infimum of the normals, right? 0 sigma. But we know that this is 0, right? Less than 0. So what is it saying about the bias then? What is it saying about this quantity? What's the rate of convergence? Right? So this is converging to, right? Think that for a large n, right? This is approximately something, let's call this some k, right? For this number here. Right? So essentially this is saying that the bias is going to 0 at a rate of 1 over square root of n. Right? But that's interesting. How we just saw an example where this goes to 0 with over n. How so? Did you make a mistake in the calculations? Here's the deal, right? Unique solution versus multiple solutions, right? Here, the whole problem appears because we have this minimum of normals, right? Which made this quantity to be strictly negative, right? If this quantity was, if the solution is unique, what happens to this right side? What happens to k when the solution is unique? There's no infimum anymore, right? If the solution is unique, there's no infimum anymore, so this is just equal to 0. So then we will be saying that, oh, square root of n, expected value of nu n minus nu star, converges to 0. Well, but does not say that the convergence is 1 over square root of n. It could be much faster, right? If the limit here is 0, we can't say this is 1. It could be 1 over n, in fact, right? It could be much faster. But if it is a positive number or a strictly negative number, then the rate is 1 over square root of n, right? So this is, it's interesting, right? So this is essentially telling that when we have multiple solutions, the bias will be 1 over square root of n. There is no way out. When there's a unique solution, it could be faster. Much faster, in fact, right? In fact, there's a paper, Güzin has a paper with her former advisor, where they actually do a bunch of, they show a number of examples where this p can be anything, right? Between half on, right? From 1/2 up to infinity, the bias could be anything, right? Or any rate. Right? So this bias can go extremely fast, but what this result is telling is that, well, the bias can only go fast when you have unique solution. If it's multiple solutions, you're doomed to the 1 over square root of n rate. Nothing you can do, okay? That's just for the bias. Of course, for the optimal solution as a distribution, we saw that the general result, right? That we saw the general result that this one, right? Still, for the optimal solutions, we have normality or conversion to something else, but we have the square root of n in terms of the actual values. But in terms of the bias, that's when the rate could be faster. Okay? Any questions? Clear so far? Yeah. Actually, I need to change the files to the next one, the session 2. So just give me 1 second. Where did you put the other one? Yeah. Okay, so let's just move on here. This is just a recap of what we had seen, right? Okay, so let's go back to our questions. So we were able to answer some of them already, right? So we were able to say, okay, we know what happens to the optimal value. We know that this convergence to the normal distribution or, infimum of normals to nu star. Turns out, although we're not gonna talk about that here, but it's possible to show that under some somewhat strict assumptions, very restrictive assumptions, one can show normality of xn as a estimator of x star. But for that, it's a very restrictive result, so that's why I didn't want to put much emphasis here, because that's in practice that's not used much. The optimality of the normality of optimal values, yes, but the one optimal solutions, not so much. I want to talk about something about the optimal solutions, not normality, but from a slightly different perspective. Okay. So again, right, this is what the experiment we did, right? For the exponential, we do multiple experiments for the same n, right? Now, what I'm going to do here is a plot of the optimal solutions of the problem, okay? Before we did the table of, or a histogram with the optimal values, right? So now we're going to do the same thing, but for the optimal solutions, right? Okay? So when you do the optimal solution, as I said, right, for this case, then those restrictive assumptions that I talked about, right, for the optimal solutions, they hold for the Niels-Wender problem. So that's why we see normality, right? So xn follows a normal distribution with mean equal to the true normal, okay? So that's good. But again, it's only in this particular simple situation that we see normality. But here what we see in the discrete case, right? That's the behavior we had already observed, right? Remember I said, well, the solution oscillated between 2 and 3. So you can see that even now, after doing 1,000 experiments, the same thing happened, right? We only get solution x equal to 2 and x equal to 3. That's quite interesting, right? So compared to this case, here we have a variety of solutions, right? A continuum of values. But here in the discrete case, it's only 2 or 3, even though we actually have a continuum of optimal solutions, right? And remember the true problem, the function is like this, right? So we actually have a whole set of optimal solutions, right? And yet, the approximating problem only sees this one and this one. Curious, huh? Right? In principle, one would expect to see anything between those two numbers, right? Why don't we ever get a solution like 2.5, for example, right? Or 2.8. This is 2, this is 3, right? Why we only see 2 or 3 consistently? Never see anything in between, right? So that's quite puzzling if you think about it, right? Shouldn't we get something in the middle? Well, is this a coincidence? No. Okay, so it turns out there is a reason why we only see this. Okay, we only see these two solutions occurring. Well, what is particular, just intuitively here, what's particular about choose 3 here, in this case? What's the property that these 2 points have? Very immediately here, right? Just looking at this set of optimal solutions, what's the property that 2 and 3 have? Are they equal to, in other words, what's the difference between 2 and 2.5, for example? What's the distinguishing feature of 2 and 3 as opposed to these other solutions? What do you think? Yeah, they're just extremes of the interval, right? So somehow, when you do the sampling, we only hit the boundaries of the set. We never hit the interior of the set. That's what seems to be happening, right? The sampling problem is never hitting the interior, only the boundaries. Right? So let's see why is that. Right? So let's talk a little bit about rates of continuous, rates of convergence of optimal solutions. Okay, just in terms of rates of convergence, right? Not, as I said, we're not going to talk about the distribution of optimal solutions because although there are some results, they are a bit restrictive, but you can still talk about rates of convergence. Okay. So in the continuous case, right, we see that x takes many values, right? They are concentrated around the true optimal solution, which is 2.23. In fact, if you see here, you can see that the values are concentrated around 2.23, right? And so that says that the probability that xn minus x star is bigger than epsilon goes to 0 fast, right? Because the normal distribution has an exponential decay, right? So the probability that xn minus x star, the probability that this is big, this probability goes to 0 pretty fast, right? Because the normal distribution goes down. So it turns out that this is true in general, okay? Not only because in this case that we see normality, but more generally, right? This kind of exponential rate of convergence, we see under fairly generic assumptions. Well, typical compactness of x. And here we need some boundness and strong convective assumptions on the g function, okay? So this is saying that for any epsilon, right, the probability that xn minus x star is bigger than epsilon, well, the limit of the log of this is some constant, okay? Well, think about, right? Well, essentially what this is saying, right? If you take the limit apart, right? And essentially this is saying that, well, I can find some constants, c and beta, for fixed epsilon. I can find some constants such that the probability that I'm epsilon away from the optimal solution is less than some, goes to 0 exponentially fast with n, right? For some given constant, right? The exponent here is a constant that just depends on epsilon. Okay? So this is essentially saying that, well, there is exponential decay, right? So the probability that we are farther than epsilon away from the true optimal solution, this goes to 0 very fast, right? This is an exponential, right? This goes to 0 with, it's a constant, and this constant is always positive, right? That's what this is saying. This constant is a positive, so this is an exponential number, so this goes to 0. As we saw, makes sense, right? At least in this case, because, right, the normal distribution has exponential decay, so if you fix any epsilon here, right, you can see that this will go to 0 fast, right? Once you take larger n, of course, you see this distribution closer, right? More and more concentrated around the true optimal value. So the probability that you are epsilon away will go to 0 very fast. Okay, that's essentially what this is saying. So, and this is still fairly general, right? So we need this strong convexity and some compactness, but other than that, well, it's still general function, right? Here we don't need any normality whatsoever, right? We don't even need normality. It's true that we are assuming uniqueness of optimal solution here to be able to get this, but again, right? So we can see this in the context of we don't need normality for that. Right? Is it clear what this is saying? Right? So essentially, the solutions are converging fast. Right? The probability that we are epsilon away in norm goes to 0 very fast. Right? So we should be close to the true optimal. So just understand where this is coming from, right? Where this exponential bounds come from. It's worth taking a look what is behind the machinery behind this is what's called large deviation theory, right? Which is a very well-developed theory in probability, which some of you may or may not have seen, but I think it's worth just going quickly through these main ideas, just to understand what large deviations is about, okay? So what's the idea, right? So imagine that you have, let's forget about the optimization problem for a second, okay? Forget about the optimization. Just think of the following problem, right? Suppose you have an IID sequence of random variables, right, with distribution P, right? Have Z1, Z2, and so on. And calculate the sample average, okay? Let's call it zeta n is just the average of the first n terms of the sequence, okay? Well, then we can say that for any real number a and t, right, we can say that the probability that zeta n is bigger than a, right, is equal to the probability that e to the t zeta n is bigger or equal to e to the ta. Everybody agrees, right? Because, I mean, this happens, right? The exponential function is monotonically strictly increased, right? So this event is exactly the same as this event, right? So this probability is exactly equal to this probability, okay? Well, but that's for any t positive and any a, right? So this Chebyshev inequality, essentially, that's, in fact, this more even simply is the Markov inequality, which is, what's the Markov inequality? It says that the probability for any random variable, right? The probability that some random variable is bigger than a is less than or equal to expected value of zeta z divided by a. This is called, sometimes it goes also by the name of Markov inequality. Okay? This is for any distribution, right? The probability that is a bound on the decay of the random variable, right? So the probability that z is bigger than a is less than the expected value of z divided by a. It's typically a loose bound, but it's a very general bound, right? It holds in the very general assumption. So that's what essentially the only thing that we are doing here, right? Because we have this equation. So, right, so I can say that this probability here is less than the expected value of the random variable. Right? Now my random variable is e to the t zeta n divided by the right-hand side, right, which is e to the ta, so gets e to the minus ta here, okay? So this inequality is true for any t and any a, right? Any t positive and any a. Well, but then I can write this, right, e to the t n, I can write this as m of tn, right? And this has a name, right? In probability theory, this has a name. It's called the moment-generating function of this distribution, right? It's the expected value of e to the tz. Right? So the moment-generating function has many properties, right? This moment-generating function, so that this is a smooth function. The derivatives gives the moments of the random variable. You know, it has a lot of properties. But here we only need this inequality here, right? The probability that zeta n is bigger than a, less than or equal to this quantity on the right side, okay? But that's true for any t. So if it's true for any t, we can do minimize over t on both sides, okay? And then what we get is the following, right? So I minimize and take the log, okay? Or the other way, I take the log and then minimize over t, right? So I'm going to look at this expression, take the log on each side, right? So the log on the right side is going to be right? So on the left side, you just have the log of probability that zeta n is bigger or equal to a, right? And on the right side, we have the log of that, right? Which is going to be minus ta, right? Plus n times the log of m, the moment-generating function at t over n. Right? Just taking the log on both sides, okay? And then what we do next, right? So that's what we get from here. And then what we do next, make a change of variables. Instead of call t prime, the t over n, we call it t prime, okay? And minimize over t prime. So what we see is that on the right side, what's going to happen, right? Once we minimize this, right, over t, right? We minimize this over t. what happens is that we get an expression like that, right? Well, because we have minus this quantity, and we are minimizing over t, the I is going to be the sup of t times that A plus the log of the moment generating function, right? That's exactly what you get from this side here, right? So sup of TA plus the log. Well, this n is going to disappear because of this change of variables, right? We take t prime equal to t over n. So this n is going to disappear. So we end up with ty, or ta in this case, minus the log of the moment generating function, okay? So, and because it's a negative sign, this becomes a supremum. We are minimizing because of the negative sign. It becomes the sup of this quantity, okay? And here we see an interesting connection with convex analysis, okay? Well, because this is nothing but the so-called the conjugate function of the function lambda, right? What's the conjugate? This is the definition of conjugate function, right? It's just the supremum over ty minus the function. Right? We can define the conjugate for any function, right? So in this case, what this is saying is that this inequality is here, what you get on the right side, this function, turns out, right, is just the definition of the conjugate function of lambda, okay? So the nice thing about this is that then one can use all the machinery of convex analysis to infer properties of this function y, this function I, right? We know it's a conjugate function. Being a conjugate function, for example, we know that from convex analysis theory, right? We know that this function is convex always, right? This I function is always convex, right? No matter how the distributions of the zetas here, this function is always convex. It has other properties. For example, this function is going to attain its minimum at z equal to mu, where mu is the average, is the expected value of the zeta, right? So this I function will be like this, right? Where the minimum is the expected value of z, is a convex function. In fact, and I of mu is equal to 0, in fact, right? So this I of mu is 0, okay? And this function will look like this. So what is this function giving us, right? Why is this important? Because this exactly is called the rate function, right? So this is saying that 1 over n log of this probability that zeta is bigger than A is less than this, the rate function calculated at the same value. So this is just, when you fix A, this is just a number. Do you agree? Right? When A is fixed, this is just a number. So that's the rate at which these probabilities, right? Think about what this is saying, that what this is saying is that the probability that zeta n is bigger than A, right? Bigger or equal to A, is going to be less than or equal to e to the minus I of A n, right? So that probability, the probability that you're bigger than a certain quantity, goes to 0 exponentially fast, and the rate is given by the rate function, calculated in A. You see what's going on, right? So, and think about this I function looks like this, right? This is the I function. So the farther we are from mu, right, the high is going to be the I of A, so the faster will be the rate, as we would expect, right? If you're taking the average of the zetas, right, and you say, what's the probability? Imagine that zeta, the true expected value is, I don't know, 0, right? And you say, okay, what's the probability that zeta n is bigger or equal to 2, right? If the true average is 0, the probability that zeta is bigger than 2, you expect that to be small, right? And it should go fast as n grows. Well, this is telling us how fast it goes to 0. It's given by the rate function. And of course, the rate function depends on the distribution, right? The rate function, it depends on the distribution through this lambda, which is the log of the moment generating function. Okay? So in a sense, this constant also gives the best rate. So the famous result in large deviations, one of the most famous results is what's called Kremers Theorem, which essentially says that, well, this is not just an upper bound. Here we just talk about this as being an upper bound, right, on the rate. Turns out that one can also, it's a bit more involved, but one can also show that a lower bound holds, right? So this is, here we have an upper bound, right? Turns out asymptotic, there is an asymptotic lower bound, which is the same quantity. So one can say that in the limit, the log of this is actually minus the rate function, right, the smallest value where I is bigger or equal to A. A is the value where you're calculating, right? So again, but this is just a constant, right? And this is equality now. So asymptotically, this is the sort of the exact rate of convergence. Okay. So just to give a numerical example here, right? So suppose we have a binomial distribution. Okay, just to give a simple example to see how these things are playing a role. I have a binomial distribution. I want to calculate the probability that z is bigger than n by 2 for p 1/3. Okay. So let's try to understand that. Why we are trying to calculate this, right? So we have a binomial distribution, right? Let's pick an n, right? Let's say n equal to 100, right? To pick one, okay? So I have a binomial. Z is a binomial. 100 and p equal to 1/3, right? So what is the expected value of z? If you have a binomial with n equal to 100 and p equal to 1/3, what's the mean? Yes, it's 100 times 1/3, right? 33.3, right? So that's the mean of z, right? So now, suppose you want to ask the question, the probability that z is bigger than n over 2. In this case, probability that z is bigger than 50. Okay? So, what do you think? What do you expect this to be? Small, right? Now, imagine, of course, you can say, okay, I can calculate this. I know this is a binomial. Okay, I can just use the form of the binomial distribution, right? Calculate all these binomial terms. Yeah, you can do that if n is fixed, right? But imagine now we want to do this for an arbitrary n. Then it's much more complicated, right? In fact, if you try to do this for n very large, any calculation is going to break down, right? Because if once then you start getting these numbers that are too small, if you try to do this usual way, right, with each coefficient to the power k and sum, no way you can compute, right? So we want to do this for general n. So instead of n equal 100, we want to, let's do more general, right? So we know that in general, if this is binomial n 1/3, the expected value is going to be just n over 3, right? And you want to calculate the probability that z is bigger than n over 2. Okay? So this probability, of course, should be, well, if the average is n over 3, this probability should be, we expect this to be small, right? Well, how can we put this in the context of large deviations, right? So what is a binomial distribution? You can think of a binomial, z, if z is binomial, n 1/3, what is a binomial distribution? Think about, right? What's the meaning of a binomial distribution? It's like we draw, right? We do a bunch of 0-1 experiments, right? I can think of this as being the sum, right? From I to n, or some variable, I don't know, let's call them bi, right? Where bi is just a Bernoulli random variable, right? Which is 1 with probability 1/3, right? And 0 otherwise. Does everybody agree? right? A binomial is just a sum of Bernoullis, right? Well, but if that's the case, then we are precisely in the setting of large deviations, right? Because now this probability means what? This is the same as the probability that the sum of the BIs, right, is bigger than n over 2, right? Which is the probability that the average of the B's is bigger than 1/2. Do you agree? So if that's the case, well, but now we know how to calculate this using the large deviation theory we just saw. Right? This is just the average. The probability that the average is bigger than something. We can apply. We know how this converges, right? All we have to do here is what? We have to calculate this rate function, and that's it, right? Well, the rate function in general is very hard to calculate, as you can imagine, right? Because this is the log of the moment generating function. For an arbitrary distribution, it's very difficult, but for the Bernoulli, it's very easy, right? So what is the moment generating function for the Bernoulli distribution? Good exercise for you, right? What's the moment generation function for the Bernoulli? Not even the rate function, just the right? If BI is 1 or 0, right, with probability 1/3, right? What is the moment generating function of this guy? Right? This is just E to BIT, right? So what is this? BI can only take 2 values, right? So this should be a simple expression, right? What is this? When B is 1, this is e to the t, right? Okay? Times the probability, which is 1/3, right? Okay? Plus, when B is 0, what is this? 1, right? So we have an expression for M. Well, if you have an expression for M, we have an expression for log of M, right? Just the log of this. And then we can think of calculating the rate function, right? So now the rate function, now it's literally a matter of solving a one variable optimization problem, right? Now we have the log of this guy, right? And now I want to solve the problem sup over t of t times 1/2, right, which is the quantity that we want, minus the log of this, right? It's just like a one variable problem. I can solve it for t, right? Can differentiate equal to 0 and everything, right? It's just a one-dimensional problem. So I'll spare you of the calculations. But here's what we get, okay? So the limit, right? We know that by the large deviation theory, the limit of 1 over n log of this, right? That's what we saw here. This is just minus the minus the minimum of the rate of function of the Bernoulli at 1/2, right? At 1/2. That's exactly what that theorem tells us, right? That's the inf of the rate function for y bigger than half, but the function is increasing, so the minimum is going to be I of half. Oh, but what is the I? Well, this is for a general p, actually, right? Instead of p 1/2, 1/3, we're doing for a general p. So you can see where this is coming from, right? This is just solving the supremum, right? You can do the calculation yourself, right? But it's just solving this problem for, now we know what the moment generating function is, then I can solve for t, calculate this optimal value, and we get this function for the Bernoulli. So we just plug in I equals 1/2, we get this expression. So for p equal to 1/3, this probability is going to be minus the rate function at 0.5. So if you plug in p equal to 0.5, we get this, right? So we know that for n large enough, the probability at z bigger than n by 2 is, it goes to 0 with this speed, 0.5. Where this 0.5 came from is just the rate function calculated at 0.5. Okay? So this is, just to illustrate how to, where this plays a role. Okay? Now, why is this important, right? Because remember, the whole reason we talk about large deviations is to understand why do we have this type of results, right? That the speed at which we get away from, we are epsilon away from the x star, why does it have the exponential form? Well, what is behind this is the same type of theorem, right? Same type of large deviation theorem, having exponential decay. Just as we saw before, right, that we could translate central limit theorems from pointwise estimates to optimal values and optimal solutions. Here is the same thing, right? We can translate large deviations results we will develop only for, average types, right? Sample averages. We can translate that into the context of optimal solutions and optimal values. Okay? So in particular for optimal solutions, it's very helpful because even without the normality, we don't need the normality, we can say there is an exponential rate of convergence. Okay? So that's what we get, right? Now, in the finite case, now let's consider a special situation, okay? Now suppose, and this will be good to understand, to see how this large deviation theory apply to the rate of convergence. I hope the idea will be more clear now, the connection between the two, right? Now, let's suppose that the feasible set is finite, right? So we are optimizing our problem, right? Our x, our feasible set x is only finite number of points. Let's say 10 points, okay? And we are minimizing g over that finite set. And we are approximating g, again, with the samples, right? With a sample average approximation. And let's suppose, again, for simplicity, that the solution is unique, right? So, because I have a finite set, right, we can say that if the optimal solution is unique, we can find some epsilon that guarantees that the optimal solution of the optimal value is less than epsilon away than any other value, right? Let's think about it. We have think of this in one-dimensional case, right? Imagine that you have our x's here, right? Only finitely many. And so because the solution is unique, imagine that our function looks like this, right? Our function looks like this, which means what? So I'm only interested in the value of the function values at those points, right? Nothing in between, because it's a discrete problem. So because the solution is unique, there has to be some positive number, right? Which is that any other solution, like in this case would be this guy, right? Epsilon, any other solution will have to have a value at least epsilon more than this. Right? Does everybody agree? Right? There has to be at least somewhere. I don't know what that epsilon is, but there has to be a positive epsilon. Right? That the solution is better. Okay. So then, now let's think about, right? Before we put the slides, let's think about what's going on here, right? So we know, so there is an epsilon here. Now we know that we can approximate each g of x. We can approximate with a gn hat of x, right? In such a way that the probability that this guy is more than some quantity away goes to 0 exponentially fast, right? So the probability that gn hat is bigger than gx plus some delta, that probability is some exponential number, right? That's what we just saw from large deviation, right? Because this guy is just a sample average of this one, right? So that probability goes to 0 very fast, right? But so what is that saying? So if I know that the probability that I'm delta away, that probability is small, that means what? That I can draw a ball here, right? And then I can say that, well, my G is essentially the same, my Gn is the same as my G in this ball, right? Which means what, right? So for each, imagine we do this for each x. We can find a ball here that we guarantee that Gn, right, is within a ball of size delta of the G of x. So if you take delta sufficiently small, then what happens, right? If I can guarantee that any Gn is within delta, some delta of Gn, what happens to the approximating problem? Let's see if you understand the idea, right? So essentially, you're saying that Gn is within delta of G, any delta that I want, right? And that probability, right, goes to 0 very fast, exponentially fast. So if this is true, that means this is going to be true here, is going to be true here, is going to be true here. So what happens to, what can we say about the Gn, the minimum of Gn, of Gn? Is the same solution, right? Why? Because we know that Gnx star, right? That star is the true optimal solution, will be less than the Gnx for any x, right? With high probability. Not with probability, but with high probability, right? Because by construction, I know that the probability that they are delta away, that probability goes to 0 exponentially fast. So the probability that this happens, right? So the probability that this happens is exponential. Oh, sorry, this is 1 minus that, right? So this happens with exponentially high probability, right? The probability that this does not happen is exponentially low, right? So this is going to happen with some high probability, which means what? That the solution of the approximating problem will be the same as the original problem. Right? Because this, think about it, the Gn is almost the same as the G function. Right? In essence, they are the same within this delta, but delta sufficiently small to make this function be, smaller than the amount to the next point. Then we get the same solution. So the solution will coincide, right, with x star as long as this holds, right? So the solution xn, if Gn is less than Gn of x for any x, right, except, of course, the star, so that's when the solutions will be exactly the same. Well, but the probability that this happens is exactly what we drew here, right? So the probability that this happens is very high, right? It goes to 0 exponential, it goes to 1 exponentially fast, right? So that's what we know, right? By large deviation theory, we know that for any x, there exists a constant, right? So that this probability is, the probability is bigger than delta, it goes to 0 exponentially fast. So the probability that they are within delta goes to 1, right? Then we can say that, putting all together, we can say that the probability that xn is not the same as the true optimal goes to 0 exponentially fast. Compared to this other result, right? Remember, initially we had seen, for a general problem, we only had seen that the probability that I'm more than epsilon away, that probability goes to 0, right? The other result is much stronger, right? We are saying that the probability that they are different goes to 0 very fast, right? Before we could just say, well, the probability that are more than epsilon away. No, the probability they are not the same, that probability goes to 0. Right? So more generally, here's what we can say, right? We can generalize this for the case of multiple optimal solutions. So what can be said is the following, right? That suppose, again, in the context of being finite, now suppose that the moment generating function is finite. So this is just so we can apply large deviation theory, okay? But this is very mild assumption, right? Supposing that the moment generation function is finite is actually very mild. It's just having, most distributions have that. So then there exists a constant such that the probability that the solution set that I get from the approximating problem is not contained in the true optimal solution is bounded by something that goes to 0 exponentially fast and depends on the cardinality of the set. Okay? Well, that's the case where x is finite. Another situation, similar situation, occurs when you have the following, right? When you have a feasible set that is a polyhedron, when the distribution has finite support, right? So it's a discrete distribution, and for every realization, and the function g is convex and piecewise linear, right? Well, what is a situation where these assumptions are satisfied? What's a typical class of problems where this is satisfied? Can you remember and recall one? X polyhedron set, finite support distributions, convex piecewise linear functions. There's a familiar case, right? Which one? Huh? Three-stage problems are exactly like that, right? The second stage function is convex piecewise linear, right? In fact, that's why you can apply all these cutting plane type methods, right? If you have now, if your distribution has finite support, meaning that you only have finitely many outcomes, right? And again, that's very often the case in stochastic programming, right? So all these decomposition methods are designed for cases with finite support, right? So though you have finitely many cutting planes, then you can do, you can prove convergence in finite time and etc., right? And well, X being a convex polyhedron, again, two-stage case, that's very easy, right? Because it's just given by linear inequalities. So it means that two-stage problems actually fall precisely into this framework, right? So for two-stage problems, turns out that a very similar result as this one can be derived, right? And what happens is the following, right? So the actual result looks like this. So suppose you have these three assumptions, right? The convexity and finite support. So let's write this event, right? Where the solution set is non-empty and is a face of the true optimal solution set, S star, right? Remember, because the problem is all polyhedron, we know that the optimal solution set, S star, is also a polyhedron, okay? That's easy to show. So what essentially is saying that, okay, what's the probability of the event that the approximating solution set is actually a face of this polyhedron, okay? So what the result is saying is that, well, the probability that this event does not happen, right? The probability that the set is empty or is not a face of this a face of the optimal solution set, that probability goes to 0 exponentially fast. Right? Now, let's go back to our Nussbender problem. Remember what the solution set was, right? In the Nussbender problem. We had S star. What was, in the Nussbender problem, what was that? Was in the discrete case, right? The discrete uniform case was the interval 2, 3, right? Well, what are the faces of this, this set? This is just an interval, right? What are the faces of this? Think of this being a polyhedron in one dimension, right? It's just extreme points, right? So now we see why we observe that behavior, right? The 2, 3. Essentially, this is saying, well, the probability that we end up at a face of the optimal solution set, that probability goes to 1 exponentially fast. And that's exactly what we saw, right? We cannot guarantee that we will converge to one point. We can only guarantee that we will stay at the face, at a face. And again, that's what we saw, right? The solution was oscillating between 2 and 3, but it's always on a face. So the probability that we are not, right? The Sn is the probability that, think about, right? The probability that Sn is not a face of S star, that probability goes to 0. No, because we have the log here, right? It's the limit of the log, right? So yeah, this is saying that if you get rid of the logs, right? So this is saying the probability that the epsilon n complement, right? That probability that the event does not happen, it will be bounded by e to the minus beta n, right? The probability that this does not happen is bounded by this, right? So again, So we see why you saw that. So in our case, the Niels-Vendor case, when it took n equal to 270, it was large enough so that this probability became essentially 0, right? Oh, I guess they are telling us to go away. Well, that's okay. At least the projector is not. The projector didn't go. But in any case, I was about to finish. It's 5 o'clock already anyway, so it's about time to. Ah, okay. Edit. Okay. Good reminder, though, right? That it's about time to close. So, yeah, but this is a good point to finish anyway, right? So. This is showing that the Niels-Vendor case this was no accident, right? So the n there, the n270 that we look, right, that only gave solutions 2 and 3, that n was so large, was large enough to make this expression essentially 0, right? So the probability that we are not at 2 or 3, that probability is 0, or virtually 0, right? So that's why we did 1,000 experiments and we never saw any occurrence otherwise, right? With a smaller n, of course, we would notice. We would see more, right? If you did the Niels-Vendor experiment, with n equal to, I don't know, 20, right? Still, you would see a lot of 2s and 3s, but you would see some other solution showing up. Maybe 4, maybe 2, or maybe 1, right? But still, the majority would be 2 and 3, right? And then as you increase n, you see this going down very, very fast. Okay? So, well, I guess that is enough for today, right? Let's see. Yeah, I was going to start talking about stochastic constraints, but then we can leave that to the next session. Okay? Questions about anything we saw today? No? So just to anticipate a little bit what we're going to do on Wednesday. So Güzin, as I said, Güzin is going to do the 3 sessions on Wednesday. And what she will talk about will be a couple things, right? So one is, as I mentioned, the case where we saw all these asymptotic results. She's going to talk about the problem from a more practical perspective, saying, okay, suppose I can only do finite n, which is right always the case. If I only have a finite sample size, what kind of guarantees do we have, right? So there are methods. She's going to discuss some algorithms that can give us confidence intervals on the optimality gap of the problem, right? So this is a very practical method that one can then use to solve a problem. You know, you apply that sample size, and then you can have some guarantees, right? So she's going to talk about that. She also is going to talk about some variance reduction techniques, right? Which mean, because here, all we have been discussing is when you have like this IID sampling, right? She's going to discuss the case where there are techniques that you can apply to reduce the variance of the estimators, right? Instead of just doing standard sampling, you can do other types of sampling, more like smarter sampling that allows you, these methods allow you to get smaller estimators with smaller variance, which of course in the context of optimization will mean you have a faster convergence, right? Those methods are very much used in practice. And the other thing she's going to talk about is, well, here we saw the approach that we saw, right? Which is like fixing the sample and solving the problem, right? She's going to, these methods are called external sampling, right? Because you're fixing a sample and then you just solve the optimization problem to get your optimal solution, right? The approximation optimal solution. She's going to talk a little bit about the so-called internal sampling methods, where you mix the optimization and the sampling, right? So you have a point, think of like you have an iterative method, right? You have a point, then you do some samples, and then you the next one. Now you generate some more samples to get to the next, right? So you increase your effort along the way, right? So there are some methods that are, again, having more like an algorithmic context there, and then what can be said about these methods and so on. So this kind of, roughly speaking, those are the 3 topics she'll be discussing on Wednesday. And then on Friday, we'll talk a little bit, well, I'll probably try to finish this discussion on stochastic constraints, right? Talking about problems with stochastic constraints, and discuss a little bit about what can we do when we have for deterministic scenario generation methods, right? So this is just based on sampling, but we're going to discuss a lot about how we can, for some problems, how you can choose the scenarios in a series, right? Nothing random at all, right? So when you can choose deterministically the scenarios, what guarantees can be given. And we will see that in some cases, especially for multi-stage problems, it's much more common that people use these deterministic models than the Monte Carlo models. Okay, so we'll talk a little bit about that on Friday. Okay. So if no other questions, I guess we are done for today.